Hello everybody, today I'm going to present the final version of the design limit plot that I was developing since a couple of months. So the first one I want to talk about is the pressure estimation of the real gas using the Abu Qasim Dranchik method. So I have made a video of basically estimation of the hydrostatic pressure, and then I have derived that exponential formula, and also I have talked about some method, ABKD method, that I called this one as in abbreviation to estimate a real gas compressibility factor, so that we could use that real gas compressibility factor to estimate the hydrostatic pressure instead of just assuming the gas as the ideal gas. So I have written a macro with a couple of lines so that I could use that macro to estimate internal pressure for my one of my burst load cases in the design limit plot. So let's go through the macro quickly. So I have defined the real gas pressure, and then this function is depending on the pressure that the source of the pressure at the first depth, and then the temperature. I keep this temperature as constant. As I mentioned, you could also vary this temperature according to the wellbore temperature profile, but I keep it constant at the same time. It depends on the specific gravity of the gas. So this specific gravity again is the molecular weight of the gas to the relative to the molecular weight of the air, which is 29. And then you have the depth 1, which is the current depth, and then the depth 2 is the target depth, where we basically are interested in finding out the pressure at the D2. So first of all, we basically start with the assumption of an ideal gas, and then we use our exponential function to find the pressure at the D2, and then using that P2, basically we are after finding some critical properties, which basically defined by Sutton relationship using the specific gravity, and we are basically after a midpoint pressure because we are after the pressure at the D2, so we need to find the mid pressure so that we can basically start iteration of the compressibility factor, so that that compressibility factor can reach a solution, and then the resulting pressure can reach a solution as well. So then we have the pseudo reduced pressures calculated with the mid pressure over there. And then we have another density reduced value. I recommend going to that paper so that you could see those constants. There's no, I think there's no need to go into the details of these functions. The functions are readily available in that paper. But what I would like to talk about is the general strategy structure of the macro. So the first your assumption with the ideal gas, then you have a midpoint pressure. With that midpoint pressure, you are coming up with a Z1. I call it Z1 is the first estimate of the real gas compressibility factor. And then with the Z1, I put that first compressibility factor again into the same procedure to come up with the second compressibility factor without finding another mid pressure. You could probably put another mid pressure in between after finding the Z1, but I think that it might be time consuming, so I go straight to the first and the second compressibility factor estimation. After the second compressibility factor estimation, then you need to find another pressure, which is basically using that exponential function again, and then you need to find another midpoint pressure. Of course, with that midpoint pressure, you are coming up with another density reduced value, and then with those values, you can find another Z3, I called it, which is the third case of the compressibility factor using that ABKD method, and then using the Newton-Raphson iteration. So Newton-Raphson iteration is basically you find you have a previous estimate of a number, and then you basically have a function divided by the derivative of that function. Um, so with the z number 3, third estimate of the compressibility factor, you go straight to z4 in the same talking, and then I called it z4 as a final estimate of compressibility factor, which I thought the four number of iterations is enough to come up with a closed solution. And then with that z number 4, you are using the exponential function that I have derived in those equations, using the specific gravity of the gas and the temperature to come up with the final pressure at the depth number 2, which we specified over here. And then I called basically the function as the real gas as the P final. So let's minimize this window first of all, or we can close this as well. So to check this macro, I have first just made a simple spreadsheet over here, and then I used the function over here, as you could see. So that was the fracture pressure at the shoe to be in line with our design of the burst load. And then we have the temperature, we have the specific gravity, we have the depth 1 and depth 2. So basically what I have done over here is I basically cross-check the macro, and then here simply I'm basically using the same methodology. So I calculate ideal gas, the second pressure, I put it here as the midpoint. I put it as the midpoint. As you can see, the initial gas pressure time plus the source pressure divided by 2, and then I continue same way, and then here you can see that I did the third iteration. In the macro it does 4 iteration plus the ideal gas, so that you can come up with the pressure. So you could see this pressure is similar to what I got in the third iteration, so that number is good to go. So over here I basically take a screenshot from my own derivation to basically cross-check that the macro is working correctly. So let's start with the general structure of the spreadsheet, of the design limit spreadsheet. It has a couple of tabs here. So it has the performance rating tab. It has the burst load tabs, of course, to calculate the profile of the burst load and the collapse load, whatever loads you have. And then I have the design limit plot. All right. So let's start with this performance rating tab. So in the performance rating tab, basically on the top I have the collapse regimes. These are the 2018 collapse regime. So you have the transition, plastic, yield, and elastic collapse regime. So I could easily find where my grade and the geometry, specific geometry casing lies on, and then I know the collapse rating from the API. This is the uniaxial one. So then I basically have the collapse pressure in the triaxial state. So I put basically a screenshot of my whiteboard when I derived this in the video part number 4. I recommend you to watch the video number 4 for the derivation. So basically it comes from the principal stresses, 3 principal stresses, and then I put these stresses in the form of something that you could basically easily replace with their formula, so that you can come up with a like a polynomial kind of formula which had a kind of a solution exists, the root exists, so that you can have a basically simple relationship of the differential pressure compares to root tension plus the backup. For the collapse is the internal pressure as the backup case. So I have a bunch of tension values over here on this column, and then I have a bunch of differential pressure calculated, corresponding differential pressure calculated on this column. So here, this is one of the additions that I have put. I could basically calculate, give a different design factor, and then basically let's see, for example, these numbers. Why it gives number here? Because of course when you change the limit, the numbers that are meaningful in this square root is changing. That's why the square root values, as you know, is below 0 is not defined. That's why some tension values aren't giving a solution when with 1.25 design factor, because your yield strength is derated because of the design factor, so that there's no strength in those high values when you increase the triaxial design factor. So same with the wall thickness. Of course, you increase the wall thickness. What happens is basically you reduce the cross sectional area, and then what happens is your stresses are getting higher, and then your corresponding differential limit reduces on this case. So, and then the next one is the burst pressure in the triaxial state. So this is again let's go to the right. So this was the whiteboard that I have presented in the part number 4. So you can go back and then watch the derivation. So this time the backup pressure is the external pressure, because it's the burst load case, which is the differential between internal and external pressure. So I put 2 lines here. So there's 2 methods. So one of them is presented in this paper. They derived it from the circle of plasticity, and then I have made the derivation from the principal stresses, and then basically the formula is different what I have basically derived with, but the numbers, the corresponding delta differential pressure numbers are exactly the same. So that's very good. And then on the next one I have the basically uniaxial design limit. I put this in a box so that I could basically pull the limits to draw the uniaxial limits in the plot format. So you could basically I could set these up, and then let's say, for example, if I say 1.2 over here, then you could see all the performance limits is going to change. As I mentioned previously, some casing some casing connections like a special ID type casings, they might have some different performance ratings on the connection. So from the body that you can account for. That's why I have this 100% connection performance over here. If it's 80%, of course, what happens is your tension and the compression limits is gonna go down. So let's change this to 100% again. And then you have the uniaxial burst, which I mentioned, 1.25 design factor of triaxial. Why it corresponds to 1.1. That's why I selected 1.1 over here. And then I'm gonna talk about in the uniaxial design limit plot how they correspond to roughly the same point. And then I selected the uniaxial collapse of 1.05. So on the right hand side, basically I have values that are basically derate the collapse rating with the existence of tension. You see there's 150,000 pounds, 300,000 pounds, and then up to 900,000 pounds of tension. So this duration as defined by in 2018 API is exactly as the same, identical to the basically the collapse, triaxial collapse. Basically you use this equation. You use this equation, the ratio of the tension to the yield strength, the ratio of the true tension to the yield strength, to basically to derate the collapse values. Well, yield strength doesn't really is reduced, but it's reduced to basically reduce your collapse rating. So how was the structure? We were finding I talked about this in I think the video number 2. So we have the tension, we have a reduced yield strength, and then with the reduced yield strength, we are finding those constants again. To be able to find the regime again in the API collapse regimes like the yield, plastic transition, etc. Then we are coming up with another collapse rating. And then here I have the table so that the plot can pull the values from this table. And lastly, on this performance rating tab, I have the semi-major and minor method. So I call this method as semi-major and minor because this was from Dr. Kuchnichki's video. So I put the link here as a reference. It basically I have it basically basic, about it's basically about transformation of an ellipse. I have shown the derivation over here on the part number 4, basically. So you have the semi-major, the biggest exists, and then semi-minor, and then you basic transform. You transform. So the original ellipse is like this, and then you transform it at the 45 degrees, so that basically if you plot it in a PSI versus PSI axis, it basically crosses at the yield strength. So for our case, we are talking about L80, and then it's 80, 80, 80, 80 over here. So I included different tab, this as a different tab as a plot, so that I could check that the numbers over here are giving correctly the transformed correct ellipse. So I have put this into 3 and 4 different sections because I wanted to quickly have different wall thickness and design factor variations. So you have here at 7.5% wall thickness 1.5 design factor. Over here you have the 100% wall thickness 1.25. Sorry, and then you have here 100% and 1 design factor, and over here you have basically 87.5 wall thickness percent wall thickness and 1 design factor. So that's the performance rating tab. I talk about this one, and this is basically the temperature profile given from the load cases. There's a visual representation. So let's start with the load cases. So load cases I originally used from the same paper. The paper number is shown on the top name. So this was frag at shoe and then full gas to surface. So that was a burst load case, and then I wanted to build the spreadsheet, build the design limit plot, and then I wanted to test how the load case would look like on the design limit plot. So first I have done this with assuming that the gas was an ideal gas. So let's start with this stuff. So I just want to talk about the structure, how the triaxial stress is calculated on the tab, and then we can go quickly to the design limit below. So you have the depths, okay. The internal pressure is, of course, is basically now in this tab is calculated as the real gas, and you could see that one over here. That one is the compressibility factor for the real gas, which is 1. So that the internal pressure is calculated from that formula. The external pressure is dependent on the company guidelines. However, on this load case, it was specified as basically above the top of cement mud bed laminol and below the top of cement mixed water. So that we simply calculate the hydrostatic. There's nothing difficult about that one. And then you have the delta pressures of the internal minus the external pressures. So then to be able to calculate the true tension profile, final true tension profile, we need the initial conditions. So initial conditions, what is it? Is the green cement case conditions. So so we can calculate the internal pressure when the plug is bumped. Just prior to plug bump, basically you have the mud in the inside, and then you have the tail lead and the mud spacer and mud above. So these two green cement case or initial conditions profiles are very easy to calculate hydrostatic wise, and then your true tension is basically simply the outer area times the outer pressure plus the inner area times the inner pressure. Of course, you have the minus on the outside to basically indicate the buoyancy there, right? So with the buoyancy effect. So you have the initial conditions, and then you calculate the ballooning force. The ballooning force was again the Poisson ratio. You have the Poisson ratio. You have the internal pressure and the external pressure. Difference between the internal pressure and the external pressure from the initial conditions to the load case, and plus you have the thermal stresses. So the thermal stresses, what we said is basically is calculated over here. I calculated over here. So if you are heating it up, it results in a compression because of that minus sign, and then the otherwise, if you are cooling, it will give you tension, and then so we calculate that one. And then as basically with some initial conditions plus ballooning plus the thermal. In this case, bending is 0, it's a complete vertical bend, and then you are ending up with the final true tension profile. So from that final true tension profile, it goes to the second line, where it's basically it converts to the axial stress using that the true tension divided by the final tension divided by the cross sectional area, and then you have the tangential stress, radial stress, and we talked about axial stress. So now we have three principal stresses. So for the von Mises yield criterion, we need to evaluate at the inner wall and the outer wall, and then whoever is bigger as a conservative function, we will take that one, the biggest stress, and then we basically take the ratio to the yield strength of the pipe, and then that's how we come up with a triaxial design factor, which is over here. So I calculate the outer wall, inner wall, tangential, outer wall radial, and then inner wall radial, and then I calculate basically the equivalent von Mises in the inner wall and the outer wall, and then here, as you can see, whichever the minimum design factor, or I take this, or whichever the highest stress, you use that one to calculate the triaxial design factor. So this was again the screenshot from my whiteboard. And then as a result, for the load case, this is the value that you are going to plot on your design limit plot. One thing important here is this one is self-explanatory, it's differential pressure from the internal to the external. However, this one is basically, you have the backup included. Here you could see the backup for the burst load case is the external pressure. That's why you have the backup included over here, because when we calculated the delta P versus the true tension plus the we are in the burst case. So when we calculate the delta P versus the true tension plus the pressure, the backup is basically true tension plus the PO. So that's the external pressure. So that's how we come up with the values of the burst load case calculated with the ideal gas assumption. So in the real gas assumption, so we have exactly the same temperatures ballooning, except the ballooning temperature remains same. So for the internal pressure, as I mentioned, I use this function to find from macro. All right, and then basically, because your pressure is different, your internal differential pressure is going to be different, and also it's going to result in a different ballooning force, because your internal pressure is also different, because you remember this difference from the initial conditions profile. Initial conditions is exactly the same because we are talking about the same semantic profile. Okay, so for example, if you want to test it, let's take a this is 0.55 SG gas. Let's take a lighter gas, and then you could see that pressure jump from 9200 to 9600 psi. So it's a lighter gas resulting in a basically higher pressure. So it was 0.55 SG. Alright. So the calculation method is exactly the same. it calculates the basic the triaxial design factor in the same procedure. So the only change from an ideal gas to the real gas assumption is macro is helping us to calculate the compressibility factor, and then we can see that that compressibility factor is resulting in a quite a higher pressure than the real gas ideal gas assumption, 8400 versus 9200 psi, and then this higher internal pressure profile is including into giving two effects. One effect is the higher differential pressure. Second one is the basically the higher ballooning force or the higher true tension profile. So I just added another tab as a green cement test. So green cement test I just defined as 7500 psi. So this is basically you bump the plug, you bump the plug with about 500 psi over the last circulation pressure, let's say, and then you take the pressure up to your green cement pressure test value. And then in this case there is no ballooning force involved because everything is green. So you just have a different true tension profile, and then there's no thermal stresses is involved as well. So this is basically just at the initial condition stage where you apply pressure to test your casing, test your casing integrity with your the shoe track and then the plugs. So and you remember we had the loss returns load case as well for the collapse load case. So the calculation method is exactly same because you have the different internal pressure resulting from the loss returns. You will have a different final true tension profile, and you have a different differential pressure formula, and then this will be plotted on the bottom side of design limit plot because it has a negative differential pressure. So after this one, what did we forget anything to talk about? No. Okay, let's go to our I think the main focus of the video is the design limit. So here let's basically do a recap of a couple of things. So this is your uniaxial compression line on the performance from the performance rating tab, and this is the perform uniaxial this is the tension limit. So again the connection might be different. That's why I have put 100% over there. That's the uniaxial burst limit. You calculated it with Barlow. At the moment it's 87.5% wall thickness, and then it's at 1.1 design factor. You could see the design factors over here, 1.1, 1.4, and then you have the uniaxial collapse, which is here is 1.05, and then you see the rating with the tension. This was exactly same as our Triaxial collapse formula, if you remember. So I have plotted the load cases here. This is basically my loss returns collapse load case. As you see, it's plotted on the lower side. It is a negative differential pressure rating from internal to external, and then I have basically burst load case of frac at shoe full gas to surface calculated with two methods. So this is basically real gas. It has a higher pressure, and then it has a slightly higher true tension, which basically was tuned minimized because if you remember above the top of cement we are taking that the average. That's a bit tuned down, I would say, but it is a higher differential pressure rating. If you remember, we had a surface pressure of 9200 versus 8400 psi, and then I put the initial conditions here. So initial conditions, I think it was calculated here. So the initial conditions to retention profile basically are put that as a basically a starting point. So we know where we are starting from. So the pressure differential is almost zero. However, you have almost 600,000 pounds over here. And down to minus 150 at the bottom of the casing, because again this is a vertical well, and then you have the loss returns, you have the real gas, you have the ideal gas assumptions, and then here you have the basically the green cement test pressure. As you can see, you have the differential over here, 7,500 psi. Okay, which is understandable above the top of the cement, because you have if you remember, you're about, I think, above the top of the cement you have basically mud on both sides. So above that one differential will be exactly 7,500 psi. And then here you have the tension. So you could see that from the initial conditions of 600, 650 with that 7,500 psi pressure, when you put it, you increase your true tension, final true tension up to 1.078 at the top of the casing. So that gives you an indication of how much additional true tension that you are basically adding. And also it as a thermal effect and also additional surface pressure of 9200 psi from this point to this point. It can give you an idea of how much additional tension you have added into the casing from an initial condition, basically as cemented profile, to a load case of bracket shoe gas to surface, including thermal and ballooning effects. So let's look at the curves now. So this one is basically the burst, triaxial burst, which basically takes the numbers from performance rating. At the moment, as you could see, it is at one design factor, 100% triaxial wall thickness. So on the last video, I have talked about basically that if you take a 1.1 design factor on the uniaxial burst with its 7.5% allowance, then it is pretty much equal to 1.25 in triaxial design factor. Likewise, if you take let's say 100% in triaxial, it will be roughly come down to 100% wall thickness calculated with Barlow equation, uniaxial burst. Why? Because radial stress is small, and also although the value is still there, and also the thin wall assumption made by Barlow. So they are not exactly the same point. It's, I think, if you look at the number, it's 86 psi in the burst, and then 100% Barlow is gonna give you 9059 psi. So it's not exactly the same, but they are roughly intersecting at the same point. So with the semi-major and minor methods, as I mentioned, the bottom part falls into an identical same regime as the triaxial collapse equation, because of the principal stresses that I have basically talked in the previous video. So just go watch this video, please, and then you will find out where the solution is identical. However, the upper part of the ellipse that is drawn with semi-major and minor method is slightly off from the exact triaxial burst solution, but very accurate, so that still very accurate, so that you could basically have a couple of different scenarios of wall thickness and different design factor combinations, which might not be very possible with a commercial application. So what I want to show here is, for example, if I go back and then change, let's say, my design factor of triaxial to 1.25, and then come back here, as you see, the 1.25 exact solution of the triaxial burst and the collapse falls identical to the basically the 100% wall thickness and 1.25 design factor of the same major minor method. So they coincide as expected. And then you could see that 87.5%. So if we go back and then if we say, let's select 87.5% wall thickness in triaxial, 1.25 design factor in triaxial, basically further reduces our design limit of the triaxial into the this smallest ellipse here, and then basically your load cases are basically placed accordingly. So I'm not gonna discuss which section is acceptable or not. Either you need to do something with the casing and the grade, or either you need to do something about more discussion on the load cases, or both. But what I want to show is basically you can visualize the load cases with the different wall thickness and design factor combinations in triaxial, and if you want uniaxial in a simple spreadsheet format. So you could basically calculate another load case, and then basically show that with respect to your ellipses. However, in my opinion, that 87.5% it needs to be applied in the triaxial case, because it is there for a purpose. It accounts for the wall thickness tolerance, and design factor of 1.25 needs to be applied. As we know that the uniaxial burst isn't really a limit. It is shown on the design limit clause because you have such a big effect from the axial tension and axial compression, which basically at some point it reduces, and at some point when tension, it has a improvement effect on the burst profile. Therefore, the triaxial burst site is the main criteria. However, on the collapse side, we know that collapse is a different phenomena. It's related to diameter over thickness ratio. I think more than the yield strength. So that still the lower part, as you know, this is basically exactly the same triaxial collapse formula. So that the bottom part is relevant, and also this part, because in the compression, under compression, also that uniaxial collapse is relevant. So that we have basically covered different load cases here, which I think I forgot to talk about. So in my load cases at the moment, I have 87.5% wall thickness set, as you see, so that the limits and the load cases are comparable. Okay, so that 87.5%, if as I mentioned, it basically increases your radial and the tangential stresses, so that your equivalent von Mises stresses, the design factors will be lower, but it's kind of a thickness that needs to be accounted for in my view. And then you have the 87.5% wall thickness over here. So there's 87.5% wall thickness. So if I go to one design factor over here, what's gonna happen is I basically maximize my ellipse a little bit more. So as you see, the same major minor method, it falls pretty much identical on the collapse side, but a little bit off on the burst side. Still accurate. Gives you an idea where it lies with your load cases, and then your basically uniaxial limits. Okay, so this was the spreadsheet that I put forward. So simply, the bottom line is it is quite possible to make up or construct a spreadsheet where basically you can show your uniaxial and the triaxial limits, and then you can easily calculate the triaxial design factors and triaxial stresses using the ballooning and the thermal stresses. If you have a thermal profile and then you have a final pressure profiles. And again, I think the most difficult being calculating a gas hydrostatic pressure. We basically simply included a macro to be able to calculate the internal pressure profile of a gas of a casing originating from a gas column. Thank you very much for watching. Hope it's useful for all of us, and thank you again.